Recently, I'm watching a very interesting chapter by PeakMath, and they have covered a deep connection between Riemann zeta functions, Riemann Chi functions, and something called coefficient of Keiper-Lee from Lee criterion. This theorem is extremely deep, and it's equivalent to Riemann hypothesis, and I'm not going to prove anything here. But they also mention a table that's curated by the Wolfram project. They did a good amount of computation for the lambda n's. So I'm going to use Wolfram Language and Cauchy integral formula using contour integral to reconstruct the numbers inside this table. Here's a diagram for this very smooth Riemann Chi function. It is holomorphic, so you can take arbitrary number of derivatives. So it's mentioned in the Lee's criterion. You can see this function also has a different definition, which is used by the Wolfram project. You probably noticed that I do not have the number 2 in this expression. The 2 here only affects the constant term for the expansion. If we do not include 2, then we have minus log 2 as the constant term. But in the table, it's 0. So other than that, everything else is the same. If we run the code, actually pre-computed the result, so you can see that you have really complicated symbolic expressions for this coefficient. So that's why we want to do a numerical computation directly instead of keeping order too high. If we convert all the result into numerical values, you can see this is the result we have. The first one, you can ignore it, is the value of minus log 2. And for the other terms, you can compare it with the pre-computed values from Wolfram homepage. It's 0.023 and something, and at 52051. So you can see this is 0230 and at 52051. And you can compare the second one with the third one in line. So 314123. So these are the numbers are showing up exactly in this chart. Okay, so before we run the code below, I want to quickly help you guys review a very important idea in complex analysis. It's called Cauchy integral formula. It's documented inside a new release of a Wolfram U class called Essentials of Complex Analysis, and they have a free ebook online for you to review and work as a handbook if you want to refresh your memory. So to find the high order derivative of holomorphic function or meromorphic functions, you can actually do a contour integral for that. This is the Cauchy contour integral formula for any orders. You can. This is for the function itself. If you want to do high order derivatives, you basically need to add these terms inside your formula. Do contour integral about the point of interest, like z. It's z here, and you integrate about t. It's just a dummy variable, just like a regular calculus class. Before we apply this formula, we want to make sure that the function that we integrate is free of branch cut. So how we check that? Of course, if we want to prove that manually, it would be hard, but we have really good functions for visualization. So one is abs arc plot. So this function shows that there is really no jump if we circulate around this point of interest, z equal to 1. So it's a formula that's used here. Okay, so we want to take the derivative of s equal to 1. So it's equivalent to say that we want to using the z equal to 1 here. And the circle is a unit circle centered at s equal to 1. So here, if we take a look at this curve is we can see that there's really not much change in the color. Left hand side and the right hand side look like the same. You don't have any jump. And the other way to see that is we plot the real part of the integrand and imaginary part of the integrand separately. We actually don't have any gap between the value on the left hand side and the right hand side. Same thing applies for the imaginary part. The circle that in the z-plane is closed under the new manifold or new surface created by Riemann Xi. Okay, the next step is just plug this function right into this expression. So we can check their correspondence between the formulas and our code. So let's first take a look at the coefficient. We have 1 over 2 pi, and it's 1 over 2 pi. And there should be n factorial, but in this case, the 1 over n minus 1 factorial actually can really cancel that. And I think the formula used in to compute these values, they use slightly modified version of that, basically drop the n as well. It really does not affect criterion, because you recall that the Riemann hypothesis equivalence only says that these lambdas n should be greater than 0. So it really doesn't matter if you have exactly n minus 1 factorial or n factorial in this case. And then let's take a look at the expression. We have s to the power of n minus 1. So this is s to the power of n minus 1. And recall that the s is actually centered at 1, but the contour integral is about the points on the unit circle around s equal to 1. So this is the point that on that unit circle. Zeta minus z to the power of n plus 1. So recall that this is like the points on the unit circle centered at 1. And z is also 1. This sort of like shift the unit circle centered at 1 to the unit circle sitting at origin. This is a function exactly for the zeta minus z at origin to the power n plus 1, because it's simply e to the I theta to the power of n plus 1. Then you can safely bring the n plus 1 into the exponent. One more thing to check is that we do not have the imaginary number I in front of our integral. Recall that we actually doing integral on a unit circle. So the path can be parameterized as exp it on complex plane. And to convert a path integral into a regular integral that we learned in Calculus 1, we have to use chain rule. And we differentiate exp it with respect to t in this time. So if you take a look at this guy, it's the I here, it cancels the I here, right? And the EIT is actually this term. We have completed integral formalization and check with my pre-computed values. You can see these values are actually the same as the tabulated version. Thus, we completely and successfully recreated the values in this table. Thanks for listening. See you next time.